Okay, welcome back. We're doing lecture 4 for lecture 4. Due to the public holiday, this is a recording, so thank you for your forbearance and patience with the public holidays. And we've just got to keep moving them through because there's no weeks after this summer session to catch up, so we've got to do it now on the hop. So hopefully you've got some time available to you too to fix that up. Alright, so we're going to be having a look at some new distributions. We've got a Poisson distribution, and then we have a continuous random variables and an exponential distribution. Now what's not obvious in this is that up here we've had a look at the binomial distribution, and prior to that we were looking at discrete. So it's no coincidence, discrete random variables, and now we're going to be having a look at another discrete distribution. So the binomial and the Poisson are counting distributions. Then we think about continuous distributions and have a look at the exponential distribution, but there's a complication here in that these two are kind of linked in a way. Certainly they're used in sessions and examples in a way. So we kind of cross some land here where we're jumping between discretes and continuous. So please just keep that in mind. Binomial distributions and Poisson are the discrete type, and so all of the definitions that we looked at relate to that. Continuous random variables will have their own set of definitions, which we'll cover today, and the exponential, but then we've got this oddity here where Poisson and exponential are often used together. So I'll point them out as we go along. So the Poisson distribution, now Pois is a funny pronunciation. I'm a typical, kind of illiterate Australian boy, so my English is not at the very highest level. So Pois is poor. It's the only thing I can think of. Pois, Pois, Poisson, Poisson. You can call it Poisson, but I don't think that's correct. You can do the Google pronunciation, but Poisson. See, it's hard to get that Pois, 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 Poisson distribution. So I think that's the appropriate way to consider that name. A P distribution, I'll refer to it in the future, just to save you the angst of having to listen to me stumble through Poisson distribution. So P random variables are used to model the number of events that occur over time. Okay. Over a distance or an area, the number of events. So there's our discrete idea of counting. Maybe any integer greater or equal to 0. We may observe a period of time where no events occur. So the unit of time could be per day, per hour, per some other measure. What's another measure? We could do per day, we could do per hour, we could make it random. We could say per 7 minutes. Okay, we could make it per 0.1 of an hour, which is 6 minutes. Okay, so we could use any unit of time that we chose to suit the context. So in our modelling. Alright, so the Poisson distributions are a counting distribution. So to describe the Poisson distribution, we define a parameter lambda. Now this here should jump out at you for those of you that are recognising this easily. For those of you who are not, I'm making it point. Anytime we've got greater than 0, that means it is positive in maths speak. Okay, so when we see that, we just automatically assign to ourselves lambda is positive. Oh, so that's that translation. To be the mean number of times that the event occurs over some specified value. So it's a mean of itself. The value of the mean lambda is always specific to the interval. Whoops. So if we change the intervals, we've got to change the lambda. So the probability mass function, now you know what that means. the PMF, it's the exact one. Okay, so it's the exact one. It's the one that's going to be doing this to the random variable. Okay, so we've got that for the binomial, but now we've got it for the Poisson distribution as well. Okay, now here's the function for our Poisson distribution. E to the minus lambda, lambda to the power x over x factorial, the mean and the variance. Okay, so once we can not freeze up over the equations, the processes that we're using are similar to what we did for the binomial distribution. We're using probabilities to compute statistics. Why? Because they're easy to do. That's why we like to do them. So if we can just get past the initial parts that we need, then of course if we do a PMF, what if we do a CDF? There'll be other things that we'll need to consider. So let's do an example just using this simple one here. I'll just give you a break from me. In a large corporate computer network, user logons to the system can be modeled by a Poisson process. That's good, not a binomial one, but a Poisson one, with means of 25 logons per hour. So there's our mean and there's our unit of time. So our lambda in logons per hour is 25. Cool, pretty easy. What's the probability that there are exactly 30 logons? Thank you for using that word, because that tells me quite readily that probability, the question is asking for x equal to 30. So I can go back and use my definitional function as given previously, which is e to the minus lambda, lambda to the power x divided by x factorial. So I can use that, or I could use the corresponding r. Okay, I could use the corresponding r code. So e to the minus 25, 25 to the power 30 over 30 factorial. So we get a probability that there'll be exactly 30 logons in an hour with that lambda of 0.454 or 45 thousandths. Okay, 45 thousandths. So that was pretty straightforward. Let's see how else we can convolute things using language. What's the probability that there is no logon in an interval of 6 minutes? Oh dear. So what we've got here is now a no logon. What's the x for that? X equals, what does that mean? And the interval of 6 minutes, well, we've changed time frames. We had a time frames of hour per hour. Okay, so we need to work that out. Okay, we had in part A, we had a lambda which was 25 logons per hour. So it was 25 was the mean. That meant logons per 60 minutes. Okay, because that's an hour, isn't it? 60 minutes. I've just changed it to minutes. For this question, they're saying the logon is 6. So we have to change that a little bit. So where we've got 25 per 60 minutes, we want a fraction of the 60 minutes. We only want 6/60ths. So that's our proportion. And we're going to multiply that by 25. And when you go through and do the sum, you'll get 2.5 logons per 6 minis. Oh. So we've got to use the new one in this particular question. Okay, so I'm not crueling you. I'm not going to go through and cruel you. You practice this as much as you like. And so it makes it a bit easier for you to recognise. But our probability, now what's our probability up here? No logon. Oh, that's 0 logons. What's the probability that our random variable is 0? No logons in an interval of 6 minutes. So e to the minus 2.5, which is minus lambda from our equation, 2.5 to the power 0 over 0 factorial, which we know is 1. And so we get 82 thousandths, which we know is approximately 8%. So 8% is the probability that we know logons. So it's a pretty busy place. It's got a very low chance of no logons. So it's a big place and it's a busy place, serving a lot of places. Could be global, it could be just in a big complex. We have to open our thinking a little bit about that. Alright, so let's think about this one from another perspective. So that should be R, so I apologise for that. I did it on my slide, but I don't know why I didn't do it on this one. So that's annoying. I've put the R output on. So what's the probability that there are logins between 20 and 30? So we've got 20 and 30. That's our interval. So in this case here, we're going to take 20 less than 30. And so what does this mean now? So we're not going to include 30, we're going to include 29 though, because we did that previously, didn't we? So the probability will be, because we don't want to include 30, so we'll take everything below 29. Okay, and that'll mean that we're not quite at 30, we're just beneath 30, so that's that bit. And we're going to subtract everything below 20. So what's below 20? It's 19. So that'll pick up everything below 19. Okay, so we can pick that up and we can pull that out. So we've got 0.81789996 minus 0.133575, and for some reason my calculation wasn't done, so I'm going to do it here. 0.817896 minus 0.133, and so we get 0.684321, and so that's our probability that they'll be on that interval. So we just need to be very careful about how we construct that, because this bit says between 20 and 30. Now, there's a big difference here. I just want to make a note here that there's a big difference here between discrete distributions and continuous distributions. We haven't started doing continuous distribution, but an example like this changes when we do continuous distributions. But for the discrete ones, we've got to be careful. So it's just that in between. Alright, so there's our distributions there, and we took into account the fact that we didn't want to include certain values, and so we picked 29 and 19 to get the interval that was effectively between 20 and 30. That was the effective interval that we looked at. So a little bit tricky, that example, so I'm just making that, pointing that out to you. So discrete and continuous are slightly different approaches for that type of question. Alright, so a contamination is a problem in the manufacture of optical storage discs. The number of contaminated particles that occur on the optical disc follows a Poisson distribution with a mean of 0.1 per centimetre. So we'll do that. So the P distribution, I'm going to put that up now, is 0.1 errors. Particles on the disc cause errors. So errors per centimetre squared. Okay. The area of the disc under study is 100. Okay, so that's 100. So we're going to have to redo it straight away. Find the probability that we observe 12 contaminated particles. So the question's asking for the probability of our random variable being equal to 12. Okay. But the lambda that we want to use has to be scaled to 0.1 so that's 1 cent per centimetre squared. So kind of in there is 1 centimetre squared. So the lambda that we need for 100 is going to be 0.1 times 100 per 100 centimetres squared. Okay, so 0.1 of 100 is 10, so 10 errors per 100 centimetres squared. So our probability, we'll take that into account. So we've got e to the minus 10 10 to the power 12 over 12 factorial, just using the same equation that we've saw before, and so we get 0.0948. So the probability is 0.948. Okay, so again, looking at our Poisson distribution, now I really made an error here because this slide isn't the R. So I do apologise, but I'm going to write it in by hand, and the one that I put up will have this on it. So we'll have our D, which represents our density function, our PDF, but then we tell R that we want the Poisson distribution. We'll have it at x equals 5, please, and we'll also have a lambda of 10. So you've got to actually put these words in for R to properly process it. Okay? So that'll give you the correct answer for your R command. So I do apologise for that. It's on the one I'm using, but somewhere along the line I've missed that. Okay, so our Poisson distribution will give us the same result. Okay, and that's with a mean of 10. And if we're looking for x of 12, so that would have to be 12 too. So we better change that. So we've got an x equal to 12, and this will give us the value. Alright, so that's fairly straightforward, I think. Okay, so what I'm going to do is very quickly, shouldn't be doing this now, but it's okay. Running this up, I'm just going to open my desktop R using Anaconda. I won't use the web page one, which I'll be doing in the lab, I guess. Either or. I just want to quickly check this. So what do we got there? So we'll just go and pull that up. Now our tutorial takes a little while to load the packages. I sometimes do this, don't I, just to let you know how it all works. So it's just loading the packages. Once that's loaded, then I can press that and ask it to open a web page, and it should open a web page, which is now done. And I'll squishy this up a little bit, and I want a new R file. Give me a new R file, please. And I'm going to type in there D Poisson x equals 12, and I might not like the capital X. I might have to change that. But I like to try things out. Lambda equals 10, and it might not like that. It doesn't like the capital X, so I'm going to change that to a little x and do it again, and it's given me the same values. Okay, so that's the same values for 12. Sorry about that, because of the miscommunication there. I wanted to be sure that that was correct. So that's good. That's how you do it. It's very straightforward. Okay, so we can use our R commands to compute the values for a number of different distributions. So whether it's a binomial distribution or a Poisson distribution. We've also nominated we're going to have a look at exponential distributions. So it's very helpful to be able to do that. Find the probability that we observe less than 12 contaminated particles. So the probability is going to be using the language skills that we're developing in statistics. So x is less than 12, and so we recognize that if we're going to use the cumulative distribution, we can't put 12 because it'll include 12, so we have to go down one. And so if we did the same thing for the problem of the discs, let me just do that way. So we want to have 12 less than 11. Now that's I need to be careful now, don't I? Because that's the probability density function, or the PDF. Okay, that's the PDF. And what did I say before? That's got a D on the front, a D plus. But if I go back up, forgive me for scrolling, but if I go back up to the binomial distribution, which is in the other sheet, which I did earlier in the day, we've got the binomial distribution. It's not a D, it's a P. I think it's a P, so it's P plus. So in order to get that one out, I have to go, because if I put in 11 there, that's not the correct answer. Whoops. Okay, that's not the correct answer. That's not the right answer. So I need to change that to the cumulative. Just a subtle little thing. Doesn't like that. Okay, so you've snookered yourself now. So I've got to go to my documents. And I've got to go to the Poisson distribution. D pos lambda. Aha, see, when you change it, Q equals 2. So I just have forgotten that's all. Instead of being X, it's got to be Q. So by all means change it to P, but just change that to Q. 0.696 is the one that I wanted. Okay, 0.696 is the one that I wanted. So it's alright, I don't mind you seeing me being human and getting those things organised. 86776. I don't normally run them out during the lecture that way. I normally get them already, but today I didn't. Find the probability that we find more than 6 but less than 15. So this is an interval, and so for the interval we have to carefully construct our interval. So more than 6 but not including 6, less than 15 but not including 15. Okay, so we've got to go and grab 14. We grab 14, and then we don't want 6, so it's going to be less than 6. That's right. It's going to be, is it going to be 7 and below? 6 below. 6 below. So we get everything from 14, because we don't want 15, and we subtract everything below 6. And we can do that also. So we can take our cumulative, control copy, this time it'll be 14, and this time it'll be 6. And what we're going to do is subtract them. So we take the upper one, just use it like a maths equation, minus the lower one, exactly like I'm doing there. So that's exactly what I'm doing here. Okay, and shift enter that, and we get the result that we're interested in. So that's 0.7864, exactly as required. So that's a nice one. So this one here was 0.654, etc. And this one was 0.13014, etc. And so that's our final result. So it's possible to set them up and build them that way. That's a little bit of a trick, changing the Q I had just forgotten about, but there you go. Alright, so using R to help us navigate some of these, or we could use the manual equations, either way. But for the purposes of this demonstration, we're just giving you the data anyway. So suppose that there exists a smaller disk area with 40 centimetres squared. Find the probability that we have fewer than, so there's our English language problem. 2 contaminated particles on the disk. So the next thing we've got to factor in is lambda at 40. Now lambda at 40 is meaning that we're going to have to rescale our 0.1. So we rescaled it for 100 before, because 0.1 was per centimetre. So it's 4 per 40 centimetres. So that's our new lambda. And so we're going for fewer than 2. X is less than 2. Okay. And so then we've got that is equal to our cumulative X, everything below 2, which is 1, and so on and so forth. So we can do that again here. We can just grab one of these and compute that. Control copy, Control V, Q is 1, and the lambda would be 4. So I need to be careful of that. And changing that. And that's as required as well, so 0.0915. So because there was a change of lambda, okay, that meant that I had to change the lambda in the computation. Here you see that. So that's an important little point to remember. If lambda changed, for the others they were still a lambda of 10, so it didn't matter, but for this particular part it changed. Now I'm not going to overload you. The emphasis is not here in the distributions. These distribution information, computing probabilities and using probabilities to generate your statistics is very, very important, but the emphasis I've got for the final exam will be mainly around, the most part will be mainly around hypothesis testing, which we're still a couple of weeks off yet. Okay, so if we look at the printouts for typical printouts, if I take all of those and tabulate them, I can tabulate all of those and bring them to here. Okay, so there's our 6. We can do that for all of those. Okay, there's our 11, etc., etc., with a mean of 10. So we can do that. Here's a new one with a mean of 4. So that's why I changed that one there. Okay, so it's not terribly difficult. It's just the same use. It's just a slightly different approach. Okay, so again, we're using the CDFs in the way that we want to construct our intervals and get our probabilities out. Alright, so in this particular case, a little bit of fun. That's the same problems. So I'll leave you to look over exactly the same problems, just a repeat slide. Suppose the cars wish to pass straight through an intersection from north to south. So this is a challenging example. Again, don't worry about it. It's not going to be an exam. From north to south, arrive at an intersection at an average rate of 1 car every 10 seconds. Suppose the cycle of lights are timed in such a way that these cars must wait 2 minutes at the intersection before being given a green light. Suppose that 15 cars could clear the intersection in the direction of each cycle. What is the probability that at least one car that had stopped at the light won't get through the next pass? So we've all had that, haven't we? We've all been at the tail end of a queue, and then the light goes green and we don't get through goes orange and red again. I didn't get through the intersection. Boo. Okay, so we're actually working out the probability. So this falls into the category of traffic engineering, or if you want to look at the mathematics of this, it's operational research. That's a whole topic of its own. So at least one car, if we go back and look at our particular little pictures that we got, at least will tell us that it looks like this. So our random variable, so we can't use that because we don't have a function that does that. So what we have to do is we have to take the complement of that. Okay, so what's our lambda? Our lambda was 1 car every 10 seconds. So that's what we're told. Okay, 1 car every 10 seconds, that's good. However, the problem was couched in terms of a 2-minute wait. So we've got to rescale the timeline because we're waiting at the intersection. Okay, there's our lights. There's our waiting at the intersection. We're going that way, and we want to go from north to south, and we want it to be such that 2 minutes is the cycle. So we have to redo this. And 2 minutes. 2 minutes is what? if it's one car every 10 seconds, how many cars is it in 2 minutes? Well, 2 minutes is 120 seconds. Okay, so that's going to be a factor of 12. So it'll be 12 cars every 120 seconds. So there's a little bit of fiddling, isn't there? We could make it all about the fiddling, but I don't like to do that. Alright, I want you to experience the fiddling. Of course, that's the annoyance, the language, the retiming stuff, but for me, that's not what's important. For me, what's important is that's just ancillary skills that you use. The actual problem is the thing that we want to demonstrate. So once we've got our lambda, we're able to take the complement for a cumulative density function at 15. Okay, and so at that we'll look that up or compute that, and we'll get a probability of 15% that will get through the intersection under those circumstances. So yes, it's a very challenging example, and whew, isn't it good that I'm not going to hit you with that. Alright, so what we're going to do now is move off our discrete distributions and have a look at continuous random variables. Now, continuous random variables differ in a couple of aspects from the discrete random variables that we looked at. So I want to make a bit of an emphasis about those subtle differences because they affect the interval problems that come up. So the set of values for a continuous random variable can take on any set of real numbers. The probability distribution for a continuous random variable is specified by some function, which we call the PDF. So again, you'll look at that as the exact equal to 1. The following requirements must be met for a function to be a PDF, and that is it needs to be 0 or positive, and the total area under the curve is equal to 1. Now that's the probability, isn't it? 0 to 1. The probability that a random variable takes a value within a range under the area of the density curve of that range. So we think of the probability as an integral. Yes, that's right. So if we have a look at the integral for continuous random variables, there's something that's differing from the discretes. And the thing that's differing is this side here. If you look back to the slide that we did this in the discretes, that had not equal to. In discretes it was not equal, but look at that. It's the same. Why is that so? Okay. Notice that for a continuous random variable, where it is 0 for any specific value of a, because the area above a point under the curve has no area. So this is not true for the discrete random variable. So this is very, very important. So when we're dealing with discrete random variables, this is not true. It doesn't hold. So that's why we have to pick the next lowest one. Here, we don't have to pick the next lowest one because we're already arrived at it. Okay? So this is pretty straightforward. Typical integrations and areas under curve, there's no need for me to go through all of that as assumed knowledge. I've emphasised the important part. Now, this is not to cruel you, it's just to give you an example. The first question I always get is, where did you get the function from? Well, I'm using the notion here that a thin copper wire is like the wire that you would have inside your mouse cable, not inside your PowerPoint, but a small mouse cable. And so assume that x can take on any value between 0 and 20 with equal probability. What is the probability that a current measurement is less than 10 milliamps? So in actual fact, I'm going to apply this definition to compute the value. Okay, so I'm just going to do an integration and express it in terms of a probability. Now again, I don't want you all panicking and thinking, oh my god, we're going to have to do all of it. No, let's just get used to it. Okay, so we want less than 10. Because it's a continuous distribution, we're not going to make a distinction between less than or less than and equals to. Ta-da! Okay, we're just going to go with what's in front of us. Okay, now current is inversely proportional, so we're going between 0 and 10, and current is inversely proportional, so what I'm saying here is that the current is inversely proportional to the resistance, and so our function for current will be 1 over 20 dx. This realign. Now I won't give you this kind of problem as examinable because there's an element of physics to that that's not warranted here at this early stage of your careers. It comes later. What do you see when you see that one? What's in your mind's eye? So we're doing an integral dx. That's really the question I'm asking. What you should be seeing is 1. What's the integral of 1? Anything raised to the power 0 is 1. Therefore, to do the integration, we would have up and under. And that would be, so where before we had nothing, we now have a variable. For some reason, this is a subtle thing that gets forgotten about, and so in this case here, that's all that's going to happen. So when I do this integral, I'll be taking the constant out the front. The integral will mean that I'm going between 0 and 10 by the fundamental theorem of calculus. And so that requires our scaffolding. So we're going to bomb x everywhere there with a 10 and bomb x everywhere there with a 0. And so it becomes 1 over 20. It's just x, so it's 10 minus 0. Clearly that's trivial. So we get 10 times 1/20th, which is 10 over 20, which is a half. So the probability is 0.5. So the exercise in and of itself is to get you thinking about where it may lead. It's not for me to dump on you and panic you in terms of assessment, but to say to you, look, this stuff can lead you into a lot of different places. You're using a lot of familiar skills now, and there's some building to do in terms of contextual situations. So in terms of these PDFs, let's think about the probability density function and whether or not this particular function is a valid PDF. Now this is happening in high school these days, so you've kind of done this. If we go back to the definitions, we need these two things to be true. We need that to be positive, and we need the density of curve integration to be 1 across infinity. So that raises an interesting question about how we approach integrations across infinity, because they're a particular type of integral called improper integrals, and you haven't done those yet. So the way that we get around that is we use a piecewise, what am I doing? A piecewise domain. And that domain restriction allows us to use the general definition for an improper integral. Okay, and so what we'll do is we'll have the integral of our function, and we want that to be 1. That's by definition. The other thing we want here is to demonstrate our function is always positive. Okay, 0 or positive, and it has to be always. Okay, so the two things are required for us to present that it is in fact a valid definition. So if I put together my 1 minus y squared and go ahead and do some multiplications, they'll cancel out, so I'll get 1 minus y squared. Okay, and then I can add it because I'm not subtracting it. I don't need to change the sign. So I get to that point. What's that mean? Well, that means that y is equal to plus or minus the square root of 1, which is plus or minus 1. So that would be an interval as a result of this. Okay. Now what's our definition? Oh look, our definition was only this bit. So we have a domain that sets the limits of integration, that is positive. So it's always positive, because we're only going to take the positive one. Okay, so that's ticked. We've got that. Wonderful. Ah, pretty good, these piecewise domains. They help us out with some tricky maths, under the bonnet type maths. Alright, the next thing, of course, is the integral equal to 1. Well, we need to do an improper integral, which you guys haven't learned yet. And unfortunately, we don't cover in the course because of the amount of work we're doing in these courses. But what we've got is this piecewise domain. So what we're allowed to do is express this way. Okay. So in effect, we are not breaking any rules by doing that domain restriction. So bring it out the front. Then we'll be left with the integral between 0 and 1 minus y squared dy. Up and under on each will give us y minus y up and under between 0 and 1 by FTC. Okay, so that's not so bad. 3 over 2 outside of y minus y3 on 3 bombed with a 1 minus y minus y3 over 3 bombed with a 0. So clearly that one's out. So we're simply left with 3 on 2 outside of 1 minus 1/3. So 1 minus 1/3 is going to be 3 on 2. I haven't got my camera on, so you're not seeing me hold my head. 1 is 3 over 3 minus 1/3. So it's 2/3, so 3 on 2 times 2/3, which is equal to 1. Ta-da! So we've now met the second condition to show that it was a valid probability function. Very good. Thank you. Okay, so just a simple thing to populate these values. I won't be. I will talk more about the final exam later on before we get closer to those weeks, and I'll highlight what I want you to emphasise. I'm not just going to say everything's examinable. I have heard a lecturer tell students that. Well, good on you, bully for you for first years. I don't agree with that approach, but there you go. So that's all very straightforward. If this is something that's ailing you, what do you do with it? We haven't got know-how this week because of the public holiday, but if this is something that's ailing you, bring it to know-how and I will walk you through it. Okay? Very straightforward. Put all those values in and you will get a value of 0.442. So now we're using integration to compute probabilities. Probabilities will help us compute means, variances, standard deviations. Okay, so we're back onto that kind of trait. Don't lose sight of why we're doing probabilities. It's simply because we want to generate our statistics. So for this one here, 0.5 and 1, greater than probability 0.5 and 1. So then you go off and complete that, and the final answer is 0.3125. I'll let you complete that. Okay, so how does this change anything? Well, we've got our cumulative distribution function, our CDF. Okay, and there it is. There's our cumulative distribution function with the inequality pointing it the way we want, and we've got a definition for that. The cumulative density function for a continuous function can be used to determine probabilities. And so there's our probability. Remember, we're looking at continuous random variables. So I won't go through all of that because that's your standard definition for the fundamental theorem. But let's think about how we might compute some values. So that's not necessary, and I am apologising for doing that. But So the function here is the one that we looked at before. We could compute it. More likely, we look it up off a chart. So if it's not a Minitab, it's an R, and we look it up. So what this is saying is we can go through and say, okay, continuously uniform from 0 to 20. When x is 10, the probability is 0.5. So it represents this ID. And notice it doesn't matter because it's a continuous variable. Our function value at 10, if you want to look at it through the function idea, is 0.5. Okay, so it's fairly straightforward. We can use these to compute our means and standard deviations. So there's our mean, our expected value. It's the product of our values. We saw that before with the other distributions, and our variance likewise. There's an x squared term. Okay, it's just a 1. Okay, so in that way, they're fairly straightforward to compute. Same kind of thing, subtracting the square of the means once found. Alright, so we'll do a couple of those laborious type computations, but again, don't panic, I'm not going to make you do it, but it is something that we need to see. So the amount of time that a train is late is a continuous random variable with a PDF. There it is. Find the mean and standard deviation. So now we're going to compute the probabilities using integrations so that we can find our statistics. So our mean is the expected value of y. Change of variable shouldn't throw you. A definitional improper integral, okay, is y to f of y dy, so we need to take those products into account. So we've got a definition now for our function, 3 on 500, y, this one, times, I should put the integral in there, minus 5 to 5, we're given that here. And our f of y is our function from our definition up there, a piecewise definition. Okay, so our piecewise definition's given us this function. So that's a very, very straightforward integral. You can do the expansion to make it easier for yourself. Again, bring it to know-how. If you're concerned about this in any way, shape or form, that would be fine. So we've got the expansion gives us 25y minus y cubed dy, which is 3 on 500, 25y squared on 2 minus y4 on 4 minus 5 to 5 by fundamental theorem of calculus. And so in this particular case, what we find is that when bombing all of that with 5s, and minus 5s, that should have been a 4, over 4, and we get the same number because of the evens, so we actually get a value minus the same value, which gives us 0. The product is therefore coincidentally 0. So it's just that use. So don't panic, don't be alarmed, don't think I'm going to load you up in that way. That's not what the subject is about. It's important that you know this stuff, it's important that you see it, but there simply isn't the time to be fair to you and to be just. I want to entice you to keep studying and using your integrations and finding out about all these other techniques in the future, and you won't do that if I cruel you and make you feel less than adequate. So that's not what I'm going to do. Okay, I'm going to make sure that you see the sense in what we're doing and the method in it, and so you can adopt that for your practice as you go forward as a student. Okay, I do not want to cruel you. That is not what this is about. There's nothing to be gained by doing that. So there's no point doing that. And you can see that maths is very doable. If you've got the right guidance and the right training, then you can sit down and work your way through things in a methodical way, even for the most abstract and complicated ideas, and use them. So we've been able to generate some statistics by using probabilities, and in this particular case we've used integration to get our probabilities out. So it really is a wonderful thing. Okay. So for the next one, I'll leave you to do that as an exercise. I will give you the solutions here. So what we've got is some solutions for this, but please go through and do it just to give yourself the practice that you need. Studying off the notes is something that I've encouraged you to do, okay? And I believe that it's an important step in your development because the answers are there, and you can scrub back over the videos and see what's being said. Okay, so we've got that one, and finally we've got the standard deviation, which is the square root of the variance of y, which will be the square root of that one, whatever that is, and we get 0.244. So please be encouraged to work on those. Alright, the next thing I want to do, now we've had a look at the continuous variables, is look at a particular continuous distribution, and that is the exponential distribution. So the exponential distribution has this function. It's a slightly different equation to the one that was there for the Poisson, but they are related in the sense that the Poisson distribution with its positive mean equals the distance between successive events. Okay. Then we have an exponential distribution. So in the Poisson distribution, we counted the number of events. In the exponential distribution, which is a continuous distribution, we can work out the time between events, or the interval. So it's often used to look at those intervals and express them as lifetimes or times to failures, or inter-arrival time. So we can use the Poisson process in conjunction with the exponential process to understand what's happening with our, to model our particular equation. So in this case here, let me say if that one's the counts of events, count the events, this one's the time between counts. Oh. So that's the link. Now remember, one of them's discrete and one of them's continuous. I think that's important. The second thing I'll point out is that the expectation, or the mean, okay, is the inverse. Now this is different to the Poisson distribution. It's an inverse property, and that crops up. Okay, so we need to just highlight that for you. Alright, so let's have a look at an example of an exponential distribution. So the time between arrival of emails at your computer is exponentially distributed with a mean of 2. What's the probability that you do not receive a message during a 2-hour period? So the first thing we're told about the exponential definition is that the expectation, or mean, is 2. Lambda, for the purposes of this, however, is the inverse of that, or the I said the word inverse, but I would have preferred to use the word reciprocal. So it's 1 over 2, which is 0.5, because they're not the same. So the actual lambda that we'll use for this particular equation, inter-arrival time is greater than 2, so for greater than 2, because it's a continuous distribution, we don't need to make any distinction about the points, so we just go ahead and populate our equation, okay, and we get 2 to infinity half e to the minus a half x dx. So we'll get e to the minus x on 2. Now if that's a problem, you need to come to drop in and get some help. Now the reason that we get away in doing the improper integral is in the same way that we had piecemeal intervals for our limits. Here we've got a function that responds a particular way, and because we've got these negatives in the exponent, what happens to the negative infinity on a half component? What happens to the negative? What happens to this guy here? So what I'm saying is that in a normal exponential, it goes like this, but in this one, it goes like this. And if it's infinite down here, this function approaches 0. So this term becomes 0. So this is why we're able to do improper integrals without going through the theory, because we're restricting both the domain in one occasion when we worked out the PDF, and we're restricting the operation of the integral by picking this particular kind of function. In this case, the exponential function lends itself to it. Okay, so in this case here, that's 0, so 0 minus e to the minus 1 is simply 1 on e, which approximates to 0.3678. So again, we're able to work out the exponential. So we can use this with R. So our R command is very simple. We can do this as well. So P will give us the cumulative one, cumulative distribution, there it is. Okay, so P, and this time it's EXP, and Q again, Q for 2, and this time they, instead of using lambda, they use this thing called rate, and you have to put it in as half. Okay, so that gives us our values, or our values for the table. Okay, there's our cumulative, so we can do that, and I think I've got that there still, haven't I? So I think that would work okay. So I can grab that and just put that in as px q equals 2 in this case, comma, and then I've got to tell it rate, and I think I can tell it 0.5, and that should be okay. That shouldn't complain, and it's given us the value that we want. Okay, 0.632, which is this one, so you can see it's the same value. Alright, but just keep in mind that the question was asking for p greater than 2. Okay, smarty pants, so you just did the integration, but then you do this, and you haven't completed it, so what's the completion? Well, the completion is that because we've got to turn the thing around, we've got to take the complement, and it doesn't matter about the fact that it's an inequality, because it's a continuous distribution. So it's very befuddling when you're switching between discretes and continuous, or it can be. So it's an important point to keep in mind. 3, 6, 7, 8. There you go. So we've been able to generate that. I could have done that in there, just done 1 minus this. And it would have given me the same thing. Okay, so it doesn't matter what you're doing, you can use your R for that. So the Poisson and exponential distributions, we've already said they're not the same thing. One's a discrete and one's a continuous. If x follows such as a Poisson distribution with lambda is the number of times, or the counts that an event occurs in a fixed interval, then y following as an exponential distribution is the interval between the two consecutive events. So this is how they're used together. That is, we take the frequency in an event with a Poisson distribution, which is discrete, and then we take a period of the exponential distribution, which is continuous. So what is the probability that we receive 3 emails in an hour? So using the information that we had before, lambda was a half. We're looking for exactly 3. So we've got to use this equation as given, or we can do it by hand and compute that 0.126. Okay, so I'm going to make a point up here that this kind of integration that you're doing here is going to be in the final exam. Now, a bit naughty for telling you that, but I want you to be able to do these integrations using the exponential distribution. Okay? I don't think you should leave the subject and not be tested on that, so I'm going to test you on that. Alright, another concept is the lack of memory concept. It's a concept that will also be included in the final exam. So, but it's not the emphasis. The emphasis is on hypothesis testing, so we'll stick to that. And just about an hour up, so I'm just going to finish this couple of slides off to finish off this lecture. So this one says, given that we've got two instances, okay, two events, and they're equated this way. So this does not depend on the past behaviour. So it's sort of a concept where what happened previously doesn't make any difference with what happens next. So in the examples that we've got here, I'm not overemphasising the computation, it's the concept that I've just spoke about. Past behaviours, okay, so it's got this memoryless property. The exponential distribution has this memoryless property. That is, it's not really going to be concerned with what happened last time in terms of what it does next. So it's got that independent element to it. For computational purposes, yes, I'll just do an example. But the most important thing is it's got that memoryless property. So we've got 6. Why? Because 4 and 2 are 6. Okay, so that's a little bit of bugbear when doing that. So we can use the equivalent to compute this. 6 minus 4. And so we get x is 2. So we've got to turn that around. And I'm going to give it, which is 0.3679. Okay, so you can think about that. But mainly it's just the concept of that it's independent between events. That's all. I'm not worried about this computation at all. So I don't want you to be either. So we use its equivalent from one event to another. And so we get 2. So we know we've got to do some work to turn that around. Given. Alright. Okay, so this is an example of one that could be helpful. So we've got a production line has a lifetime that follows an exponential distribution with a mean of 150. So here's our expected value, or our mean. Our lambda is the reciprocal of that. So when we come to do what's the probability that the machine has not broken down after 50 hours, so we're greater than 50 hours, we're simply doing an integration between 50 hours and infinity. Why are we able to do that? Because we've got a function that specifically works to minimize as it approaches infinity, which is what the exponential function does. So we're being a bit crafty in getting students to do improper integrals without proper explanation. It doesn't sit well with me, but there's a whole lesson that we would need to go through for that, and we've been doing it for a number of years, so it's fine. As long as we understand the exponential goes to 0 at infinity by FTC, you idiot. So that's no problem. So again, we end up with... Now, why am I asking you to do that one? Because I'll tell you why. Because that integral, this integral here, a lot of students still can't do U substitutions. Okay, forget about the infinity part, just doing the U substitution. And really, that's very important that you're able to do that in your career. So that's why I'm reintroducing it there, even though it's assumed and I shouldn't have to do it. But there you go. Alright, so there's our probability that the machine hasn't broken down after 50 hours. Again, probabilities are helping us to work out our means. Again, that's probably important to be able to do that kind of thing, so I'll emphasize it. For this one here, not so much, but again, it's just that memoryless property where we've got our values of events happening. What's the probability of A given B? And the probability of A given B occurs this way. And with more time, we'd spend a bit more time on that, but we're going to just go through it like that. What can we say about this? It's the same. If you'll notice, that value is the same. And this is due to the memoryless property. Of the exponential distribution. Okay, so that's it. Alright, so we managed to get there. Sorry about the longness of this couple of lectures I've put in, but we've gotten through that. So I apologise for the public holiday and the constraints of this semester, but when you're working over summer, you're going to get some online work. So I encourage you just to work your way through that. Alright, thanks very much everyone. Bye now.